All right, so today we're going to talk about the mole and molar mass. The mole is related to Avogadro's number, which you may be familiar with. We're going to also deal with calculating and using molar mass. We're going to convert between mass, moles, and number of items, often atoms or molecules. All right, so the mole, oftentimes this is a confusing topic, though in our daily lives we actually are quite used to the idea that a word can mean a number. So a pair of objects we know is two objects. A dozen means 12. A gross, you may not know, but means 144. But a million, a trillion, so on and so forth. A mole just indicates the number of objects, whatever it is you're referring to. But the value is really, really high, 6.022 times 10 to the 23rd objects, a huge number, okay? But when you hear the term mole, think of dozen, right? Think of a pair, something like that. It maybe will make it less confusing. You can talk about a dozen of many different items. The same thing is true for a mole. A mole in and of itself needs to be talked about with respect to something. So you can have a dozen shoes or a dozen donuts. Same thing with a mole. You can have 1 mole's worth of atoms, or 1 mole's worth of electrons, or 1 mole's worth of molecules. Okay. It's often used in chemistry because we often deal with lots and lots of really, really tiny things, atoms, molecules, etc. So this, and you're going to see the significance of this particular term, but 6.022 times 10 to the 23rd, that is Avogadro's number. Okay, so a mole, it's a counting group, that's all it is. It's defined by the number of atoms in exactly 12 grams of carbon 12. So this will make it very useful when we're dealing with the periodic table. Okay, so Avogadro's number, that is that 6.022 times 10 to the 23rd objects. So again, you order a dozen donuts, you're asking for 12 donuts. If you were to order 1 mole of donuts, you're asking for 6.022 times 10 to the 23rd donuts, right? Whatever it is you're referring to. So a mole of something is that number of that something, okay? So this means that we can set this up for our dimensional analysis. I've mentioned it before, but in this class you're often going to have a lot of these topics are simply adding new ratios that we're going to be using in our dimensional analysis. So 1 mole of, let's say, molecules equals 6.022 times 10 to the 23rd of those molecules. Since this equivalency can be set up, we can write that as either 1 mole of objects divided by 6.022 times 10 to the 23rd objects, or vice versa. Again, mole means 6.022 times 10 to the 23rd. So whatever's listed after it, it can be anything. You're going to find there's specific things that we care about more, but a mole simply means 6.022 times 10 to the 23rd. So we can just replace that in an equivalency to indicate that that's how many items we're referring to. Okay. So with these ratios, we can convert between things like moles and number of something, or go from number of something back to moles. So here's some sample problems doing just that. So again, you can go ahead and pause the video and try and do A and B on your own here. But your human body contains roughly 30 moles of calcium. So we can then go from moles of calcium to the number of calcium atoms. Okay. So let's start with that. Again, dimensional analysis, we're going to start out with 30 moles of calcium. And what I'm aiming for is number of calcium atoms. So this is how I would set up the problem initially. Then, of course, secondly, I would write the ratios that I think would be of use. We just saw those on the prior slide, so I'm not gonna write those out explicitly. But remember, 6.022 times 10 to the 23rd calcium atoms equals 1 mole of calcium. 1 mole of calcium. Okay, so we can use that to convert between moles of calcium and number of calcium atoms. So we can just put that in that second location, right? So we have 30 moles of calcium, and our moles will cancel, leaving us with calcium atoms left over. Again, we're never going to have 6.022 times 10 to the 23rd moles of anything, right? Mole means this huge value. So for this to be equal to 1, the 6.022 times 10 to the 23rd needs to be on the opposite side of the line as our moles. Okay, you can see moles will cancel, moles of calcium. Since I was talking about calcium down here, I'm talking about calcium up here, right? If it was a donut, it'd be a donut. So here I have moles of calcium atoms. So up here I have this number of calcium atoms, right? Okay, so this is how we would get to calcium atoms. So we should have a massive, massive number. 30 is a very reasonable number to deal with. And that's part of the reason why in chemistry, we use moles. And so then you have relatively small values that you're dealing with instead of always talking about times 10 to the 23rd, times 10 to the 25th, number of atoms. So if we were to plug all that in, we'd get 1.807 times 10 to the 25th calcium atoms. Now, typically when we do this, again, I will ask you, is this a reasonable answer? Okay. Now, you had more than 1 mole of calcium atoms. A mole is times 10 to the 23rd. So if our final answer is above times 10 to the 23rd, which it is, it must mean we had more than 1 mole to start. We did, in fact, have more than 1 mole. We had 30. So it seems like a pretty reasonable answer. Similarly, calcium atoms, they're tiny. So you can have huge, huge quantities of calcium atoms. So times 10 to the 25th calcium atoms is massive. Remember, times 10 to the 25th means you're moving that decimal place 25 times to the right. So it has 25, essentially 25 zeros associated with it. So trillions and trillions, of atoms, right? Just a huge amount. So it's very reasonable to have that value as a final answer. Okay. All right. We can also do the exact reverse. Let's say we started with a certain number of calcium atoms. In this case, 1 times 10 to the 20th calcium atoms. And we're going to try and convert that to moles. So we'll do the exact same setup. We'll start with what we're given, 1.00 times 10 to the 20th calcium atoms, and we're aiming for moles of calcium. Then you can see we can use that same ratio, just inverse, to convert. So we will take that divided by 6.022 times 10 to the 23rd calcium atoms. Our calcium atoms will cancel, leaving us with moles of calcium. Okay, after we do that, we should get this value, so 1.66 times 10 to the negative 4th moles of calcium. Now does this seem like a reasonable answer? Remember, mole is a massive, massive amount of calcium. So it's a huge amount of calcium in comparison. It means 6.022 times 10 to the 23rd calcium atoms. So it's quite a lot. And this is a small fraction of a mole. Now I'd ask if that makes sense. And the answer is yes, because we were just times 10 to the 20th calcium atoms, where a mole is times 10 to the 23rd. So we should be a small fraction of a mole. This ends up being a small fraction of a mole. Now some of us, I'd encourage you all right now to pause and type this into your calculator and make sure you can get this value. I'm very willing to bet that many of us will not get this answer. So go ahead and type it in. I think some of us are going to get this value, 1.66 times 10 to the 24th moles of calcium. Remember, you need to use the parentheses in the denominator. So what you ended up doing is you did 1 times 10 to the 20th, you divided by 6.022, and then accidentally multiplied by 10 to the 23rd. Because you didn't put this in parentheses, you didn't divide by both of these, you ended up multiplying by 10 to the 23rd. So you ended up getting times 10 to the 23rd and a times 10 to the 20 together, which gets you up in this times 10 to the 42nd. Now times 10 to the 42nd moles of calcium, I mean, this would be more moles of calcium than there are atoms in the universe. It's absolutely nonsensical of an answer. So you got to check your answer and make sure that this makes sense, okay? You could never have times 10 to the 42nd moles, right? Moles is already a huge unit. So you absolutely should never have this sort of setup. Now, if you had this many atoms, that's starting to get closer to appropriate, right? You can have times 10 to the many atoms. You could never have times 10 to this many moles. Okay, so just make sure you're using those parentheses in the denominator when you're setting up that in your calculator. All right, so now we're going to talk about molar mass. Sometimes this is written as a scripted M, And you'll see me write it as a scripted M, and then in the subscript I will write what molecule I'm referring to. So the molar mass is the mass in grams of 1 mole of a substance. This is used to convert between grams and moles. This is really convenient because a lot of times in the lab setting, we're dealing with the mass of a particular molecule, a mass of a compound. But when we're doing chemical reactions, we care a lot about how many of those chemicals are around. So you're dealing with moles. So converting between grams and moles is going to be this very central feature of chemistry. We really want to determine how many moles there are, but we measure things in mass. So this conversion is really convenient and important. So determining the molar mass, by definition, the mass of a mole of carbon-12 is exactly 12 grams. Again, carbon-12 is a particular isotope. If you look at the periodic table, you'll see the atomic mass of carbon is 12.01. But again, remember that was because there was about 1% of carbon naturally occurring is carbon-13. So the molar mass of carbon is numerically equal to its atomic mass. So that is true. Atomic mass was written in atomic mass units, AMU, but its molar mass is going to now be this new unit, though it's an equivalent in value, is grams per mole. So if you look at calcium on the periodic table, calcium is 40.08 atomic mass units for its atomic mass. That means that its molar mass is 40.08 grams per mole. So again, this is 40.08 grams of calcium per mole of calcium. And that's probably the better way to write it, because we're going to be using this very frequently in dimensional analysis. You guessed it, right? So it's okay to write out 40.08 grams per mole in one line like that, but once we're going to use it in in dimensional analysis, we're going to want to write that as a fraction. Again, we could look at sodium, 22.99. That means sodium, if you had a sample of sodium, and that sample of sodium was 22.99 grams, you would have 1 mole of sodium. 1 mole of sodium is 6.022 times 10 to the 23rd atoms of sodium. Okay. All right. So we did this for atomic mass, so we did this for individual atoms. The same is going to be true when we're dealing with this with molecular or formula masses in AMUs. So we're going to be able to, if we had things like sodium chloride, we could take the atomic mass of sodium plus the atomic mass of chloride, and you would be able to then get the formula mass. Well, the formula mass is in AMUs. You can convert that to the molar mass by simply changing the unit to grams per mole. They're numerically equivalent. So we kind of already have skills in this territory to be able to move forward. But now we kind of have a new unit that can be given to us by taking a look at the periodic table. And that's grams per mole. It'll be very convenient for interconverting between grams and moles of a particular compound. Okay, this is how you interconvert between them. A lot of times I get students asking quite a bit, how do you know whether you divide by or multiply by the molar mass? How do you know if you divide by Avogadro's number or multiply by Avogadro's number? This is kind of the whole setup. This doesn't even matter at all. I don't care about this at all. Use the units. The units will tell you very explicitly whether you multiply or divide. A lot of us will try and remember, oh, if you have grams, I have to divide by the molar mass to get to moles. Don't do that. Don't worry about any of that. Just use the units. It'll tell you whether you have to divide or multiply. Okay? So let's try some of these. Determine the number of moles of carbon in 10 grams of naturally occurring carbon, and be the mass of 0.905 moles of sodium chloride. So step 1, write what you know. We have 10 grams of carbon. We're aiming for moles of carbon. Again, this is naturally occurring carbon, so we can use the periodic table. It's not a specific isotope of carbon like carbon-12. Recall carbon-12 was exactly 12 grams of carbon per mole. Naturally occurring carbon, we use the mass, the atomic mass on the periodic table. So we could look that up and see that that's 12.01 atomic mass units, again, which means 12.01 grams per mole. So the way that we would preferentially write that is 12.01 grams of carbon per mole of carbon. Or for every 1 mole of carbon, you have 12.01 grams of carbon. Okay? So I think you can see we could get grams of carbon to cancel, and we'd be left with moles of carbon if we plug that in. So you can put that in there. This is a similar sort of thing. People will ask, oh, do you multiply or divide? Or you kind of try and remember whether you multiply or divide. Don't do that. Just use the units here. You can see grams of carbon will cancel, and we'll be left with moles of carbon. I'd also ask that you look at this final answer, see if it makes sense. We have a little bit less than 1 mole of carbon. Now looking at the problem, I think this makes sense. We had 10 grams of carbon. We know that about 12 grams of carbon is 1 mole. So it makes sense that we have just a little bit less than 12 grams. So we should have a little bit less than 1 mole of carbon. So this is how you would go about converting between grams of carbon and moles of carbon. Secondly, we can do this for sodium chloride. We have to get the formula mass of sodium chloride. So 22.99 plus 35.45. So sodium was 22.99. Chloride 35.45. And this is in grams per mole. So again, we can write that out. 58.44 grams of sodium chloride per mole of sodium chloride. Now we'll do that same sort of setup. 0.905 moles of sodium chloride, aiming for grams of sodium chloride. This time we are multiplying by 58.44 grams of sodium chloride per mole of sodium chloride. So our moles of sodium chloride will cancel, leaving us with 52.9 grams of sodium chloride. So in this case, we have a little bit less than 1 mole of sodium chloride. And 1 mole of sodium chloride is 58 grams about. So the fact that we have 53 grams of sodium chloride makes sense. We're a little bit less than 1 mole. Let's try a few more here. Determine the number of water molecules and the numbers of hydrogen and oxygen atoms in 3.26 grams of water. So here we're trying to do multiple things. We're going to be dealing with moles and converting from grams, but now going all the way with Avogadro's number from moles to number of items, number of things. In this case, number of water molecules, or even number of particular atoms in those water molecules, like hydrogen and oxygen. I'll say this quite a bit as well. A lot of times, the mole is kind of the common unit in chemistry. So if you don't know where to start, a really good starting point is just convert what you have into moles. And that'll often help elucidate the path forward. So here we're starting with 3.26 grams of water, and we are aiming for a number of water molecules. So we need to get the molar mass of water. So here again, this is that scripted M that I'm going to use with the subscript H2O. So this is the molar mass of water. So we'll take 2 times the mass of hydrogen plus the mass of oxygen, which gets us 18.02 grams per mole. Again, it's okay to write it like this. Preferentially, of course, in the problem, we're going to be writing it like this. So I'm writing it more explicitly here. So if I have 1 mole of water, I know that that's 18.02 grams of water. If I had 18.02 grams of water, I would have 1 mole of water. So this is the setup that we're going to be using. So I can use that to figure out how to convert from grams to moles as an intermediate step. So grams to moles as an intermediate step, I'll use that ratio like so. So my grams of water will cancel, leaving me with moles of water. Now, lastly, this didn't ask for moles of water, it asked for number of water molecules. Moles and molecules are not the same thing, okay? So you can't abbreviate molecules as MOL. MOL is the abbreviation for mole, which is kind of funny because MOLE is the whole word. But this is for whatever reason how this works. So we need to convert from moles of water to total number of water molecules. Now this is using Avogadro's number. Remember, 1 mole of anything equals 6.022 times 10 to the 23rd of that anything. So I can put 1 mole in the denominator here for moles to cancel. Therefore, up here is where I need to put that super large number, Avogadro's number, 6.022 times 10 to the 23rd water molecules. And this would get me to number of water molecules. So now, if you type that into your calculator, you should get 1.09 times 10 to the 23rd water molecules. I'll ask that this makes sense. Well, I see that it's 18 grams of water per mole of water. We have less than 18 grams of water. So we should have less than 6.022 times 10 to the 23rd H2O molecules. And we do, right? It's about 6 times less. This is about 3.226 is about 6 times less than 18. So yeah, this is about right, okay? That makes sense. I have 10 times 10 to the 23rd. I can have a huge value like this because we're talking about individual molecules. Again, I could never have a huge value like this if I was talking about moles of water, okay? Here I only have a fraction of a mole of water, right? Like roughly 1/6 of a mole of water. All right, now another thing that we can do is we know what water is. It's H2O, so we could convert between number of water molecules and a number of atoms that we're referring to. So every one water molecule has one oxygen atom. So I would have 1.09 times 10 to the 23rd oxygen atoms. That would also be true. Now, if I were to convert to hydrogen, I'd have to multiply this by 2 because for every one water molecule, I have 2 hydrogens. So just keep that in mind. Here we'll deal with the second problem. Determine the mass of 7.92 times 10 to the 19th carbon dioxide molecules. So I'd write in carbon dioxide molecules, get the molar mass of CO2, so 12.01 plus 2 times 16, so 44.01 grams per mole. That's 44 grams of carbon dioxide per mole of carbon dioxide. And so you take a look at this first step. We're aiming to grams of carbon dioxide. We're starting with molecules, so first get it to moles. We'll use Avogadro's number. CO2 molecules will cancel, leaving us with moles. Then lastly, we'll use the molar mass here, converting from moles to grams of CO2. So we're just doing exactly opposite of what we did in that first problem. So this is what this looks like. We're using this molar mass here to convert, and we get 5.79 times 10 to the negative 3 grams of CO2. So a small fraction of a gram of CO2. So does this make sense? Go back and look. Well, we have significantly less than 6.022 times 10 to the 23rd, right? We're, like times 10 to the 4th away. So like 1/1000th. So we should be close to like 1/1000th of a gram, and that's what we end up having, right? Close to 1/1000th of a gram. So that makes sense. Again, if anyone got this, 5.79 times 10 to the 43rd grams of CO2, your mental math should check this and say that that's nonsense. That's way too many grams of anything times 10 to the 43rd. And if you look, again, you should see that I should have less than 1 mole of CO2. So I certainly should have less than 44 grams of CO2. This is way bigger than grams of CO2. Again, you did not put the denominator in parentheses. I cannot stress enough that you need to be doing that. And then just doing the quick mental check. So if you did that quick mental check, you'd see, oh, that's a totally nonsensical answer. I need to go back and make sure I typed it into my calculator correctly. And it happens to us all. It happens all the time, right? You accidentally write minus instead, you accidentally hit the minus sign instead of the divide sign or something like that. Just a little thing like that. Just don't believe the number that gets spit out of your calculator. Make sure you check that value real quick right at the very end. All right, so the mole and molar mass. So you have an empirical formula from the percent composition. So we talked about mass percent composition already, and we can actually tease out empirical formulas from that using this idea of mole and molar mass. So we can use experiments, get experimental data to actually determine the percent composition, and then from there determine the empirical formula of a compound. Now, empirical formulas are related to the actual molecular formulas, and we'll need a little bit more information to actually do that transition, but empirical formulas still give us quite a bit of data. So if we knew the mass of each element in a particular sample of a substance like carbon dioxide, we would be able to actually determine the empirical formula of that substance using these concepts of mole and molar mass. One common practical way of doing this is with this common technique called combustion analysis, in which we can actually determine the empirical formula using some of these skills that we're dealing with. So next time we'll be talking about combustion analysis.